100 kilometers above the surface of our world, there exists no fence, no wall, no visible frontier, only an invisible threshold where air gives way to vacuum, where blue fades into black. This is the Kármán line, the formal edge of space, and it marks the boundary between everything humanity has ever known and everything we still struggle to comprehend. For centuries, that line remained unreachable, a mathematical idea more than a destination. Yet, in less than a lifetime, humankind has not only crossed it but learned to live beyond it. The dream of flight that once belonged to myth and imagination, Daedalus, Icarus, the fire of Prometheus, has become the domain of engineers, scientists, and explorers whose courage is measured not in miles traveled, but in the preparation and patience required to defy gravity itself. Today, more than 400 men and women, astronauts, cosmonauts, takenauts, have ventured beyond that thin blue line. They come from nations once divided by politics, by war, by language. They are test pilots, scientists, engineers, teachers, and even tourists. Yet, for all their differences, they share a single title: human beings who have left their planet behind. But what does it truly mean to become one of them? What kind of mind, what kind of body, what kind of soul is required to live and work in the most hostile environment imaginable? As Canadian astronaut Chris Hadfield once said, "An astronaut's life is one of preparation and simulation and anticipation, and only rarely, almost never, is it about flying in space." Behind every mission lies a hidden world of discipline and endurance. Years spent in underwater laboratories, frozen caves, desert isolation chambers, and vast neutral buoyancy pools where astronauts rehearse spacewalks in silence. They train not for hours or days, but for years, to repair complex systems, to survive emergencies, to think clearly when oxygen runs low or alarms scream in the dark. From Cologne to Houston, from Star City to Tsukuba, the journey to space begins not with a launch, but with a long series of lessons about what it means to be human under pressure. To train for space is to accept a paradox. To be prepared for the most extraordinary experience of your life, you must first learn to live in monotony. Every checklist, every drill, every simulated failure builds the reflexes that might one day save your life. And yet, for all its rigor and science, the call of space remains emotional, even spiritual. Those who have looked down upon Earth from orbit describe the experience as overwhelming. The sight of continents wrapped in swirling clouds, the paper-thin atmosphere glowing like an eggshell around a fragile world. "Our planet," one astronaut said, "looks both eternal and impossibly delicate. You can't look at it without realizing how vulnerable we are." This documentary is not merely about machines, rockets, or the mechanics of launch. It is about the human story of spaceflight, the people who cross that invisible border and the thousands who prepare them to do so. It is about courage born from repetition, discovery forged in pressure, and the quiet realization that beyond that faint line in the sky lies not only the future of exploration, but perhaps the future of humanity itself. Because the question remains, as we push further into the cosmos, from orbit to moon to Mars, are we truly ready to live beyond our home? Or have we only just begun to understand what it takes to cross that most human of frontiers? The space between curiosity and survival? Part 1. Becoming an astronaut, it begins not with the roar of engines, but with a decision, often made in childhood, sometimes by accident, always against the odds. To become an astronaut is to choose a life of near impossible probability. Statistically, you are more likely to win an Olympic medal than to be accepted into a national space program. Yet every year thousands still apply. The road to orbit is paved not only with intelligence but with endurance, humility, and the willingness to spend years chasing a goal that may never come. The first astronauts, those early Cold War pioneers, were test pilots and military officers, men trained to fly faster and higher than anyone before them. They lived in a world of risk, rivalry, and record-setting, each flight a duel against physics itself. But as space exploration matured, so too did the definition of who could go. Scientists, engineers, medical doctors, teachers, and even politicians began to join the ranks. Today's astronaut corps is a microcosm of humanity. They come from every continent, speak dozens of languages, and bring with them not only technical expertise but the ability to collaborate, communicate, and lead. What binds them together is a shared pursuit of something larger than themselves, the drive to understand our place in the universe. Still, the path to earning those symbolic silver wings is as unforgiving as the vacuum itself. Candidates must first survive an exhaustive selection process, one that tests every aspect of their being. Physical fitness is only the beginning. Astronaut hopefuls are evaluated for cardiovascular endurance, strength, eyesight, hearing, and resistance to motion sickness. They must prove they can withstand high G-forces, survive prolonged confinement, and adapt to zero gravity. But just as important is the mind. Candidates undergo psychological assessments designed to measure emotional stability, teamwork under stress, and the ability to function in isolation. The slightest weakness, impatience, impulsiveness, or inability to cooperate can end a dream instantly. Bravery is a useful trait, one instructor remarked, but discipline is non-negotiable. Those who pass the initial tests face years of intensive training. At the European Astronaut Center in Cologne, Germany, they begin by mastering the fundamentals, orbital mechanics, spacecraft systems, and emergency procedures. They learn to disassemble and repair life support modules, operate robotic arms, and troubleshoot power systems that cannot afford to fail. It's a kind of apprenticeship in survival, both technical and psychological. Underwater training tanks simulate the sensation of working in microgravity. In these giant pools, astronauts rehearse extravehicular activities, EVAs, wearing full spacesuits while technicians monitor their every move. Each session lasts 6 hours or more, pushing both body and mind to the edge. It's exhausting, repetitive, and vital. Mistakes made here in water would mean death in space. Isolation training is equally essential. In Sardinia's vast cave systems, European astronauts spend days underground, cut off from sunlight and communication. In the Aquarius habitat off the coast of Florida, they live and work underwater for weeks at a time, conducting experiments and rehearsing missions. These environments teach one crucial lesson. In space, teamwork is survival. You depend entirely on the competence and calm of the people beside you. Training is relentless, 3 to 5 years of constant travel between continents and facilities. Houston for NASA operations, Moscow for Soyuz systems, Tsukuba for Japanese module procedures, Quebec for robotics. Astronauts joke that they orbit Earth long before they ever leave it, crossing the Atlantic so often they lose track of time zones. Through it all, they study, memorize, and repeat. They practice for the disasters they pray will never happen. Fires, decompression, ammonia leaks, computer failures, even emergency landings in frozen tundra. Every checklist, every simulation prepares them to respond automatically when reality defies expectation. "We train until there is no panic left," one veteran said. "When something goes wrong, you don't think, you act." But perhaps the most humbling part of becoming an astronaut is learning patience. Most will wait years, even decades, for a single flight assignment. Some will never make it to orbit. Yet almost all of them describe the journey as worthwhile, because the process itself reshapes them. It forges a kind of resilience few will ever need but all can admire. For those who finally do hear the words, "You are flight assigned," the world changes in an instant. Everything, every cave, every classroom, every pool, every simulator has been leading to this. The countdown begins not at the launchpad, but in the quiet of their own heartbeat. In that moment, as they prepare to cross the line between Earth and the unknown, one truth becomes clear. An astronaut's life is not defined by the hours spent in space, but by the years spent earning the right to go. Part 2. Training for the impossible. Before an astronaut ever sees the stars, they must first learn to survive on Earth, in environments designed to break them down, test their limits, and rebuild them stronger. Space may be the ultimate destination, but the journey there begins in classrooms, laboratories, and hostile places that mirror the void above. Every lesson, every exercise, is a rehearsal for the unknown. At NASA's Johnson Space Center in Houston, Texas, a day of training can resemble organized chaos. Crews move between buildings like actors on a sprawling stage, each room simulating a piece of the International Space Station. There are mock-ups of every module: American, European, Japanese, Russian, complete down to the smallest valve or switch. Inside these replicas, astronauts rehearse everything from the mundane to the catastrophic, maintaining life support systems, conducting science experiments, repairing power lines, and responding to depressurization or fire. Simulations are the backbone of their education. In one exercise, 6 trainees sit strapped inside a Soyuz capsule simulator, facing an emergency re-entry. The oxygen readings drop, lights flash red. A voice in Russian fills the cabin with rapid instructions. Each trainee must react instinctively, switching systems, calculating descent angles, translating commands, all while their pulse races. It's a test not of knowledge but of composure. Panic is just wasted oxygen, one instructor tells them. The Neutral Buoyancy Laboratory, a vast pool the size of a football field, offers the closest experience to microgravity available on Earth. Beneath its surface lies a full-scale replica of the International Space Station. Astronauts, sealed in 300-pound suits, spend 6 hours underwater practicing spacewalks, their movements slowed by the water's resistance. Every motion is deliberate, turning bolts, handling cables, deploying panels. The water's silence magnifies every sound: the hiss of air, the thud of tools, the rhythmic crackle of radio chatter. After hours of exertion, muscles burn and minds fade, but discipline holds. Instructors float nearby, monitoring heart rates and breathing patterns. Engineers on the surface observe via cameras, noting every motion and error. A wrong twist of the wrist could snap a tether or damage a vital connector. Underwater, failure is an inconvenience. In orbit, it could be fatal. "We want them to fail here," says one supervisor. That's how they learn not to fail up there. Training also means learning the art of adaptation. In Sardinia, Italy, the ESA's Caves program teaches astronauts to operate as a team in isolation. For 6 days, they navigate dark, labyrinthine tunnels, relying on headlamps, rope lines, and one another. The cave walls drip with condensation. Communication is limited. Time becomes meaningless. They map new passages, collect rock samples, and record every move, an exact parallel to planetary exploration. By the end of the week, the team is bonded by exhaustion and trust. Another form of isolation takes place under the sea. NASA's NEMO program, the Aquarius Reef Base, off the coast of Florida, serves as an underwater space station. Astronauts live there for weeks at a time, conducting experiments, managing confined quarters, and practicing simulated extravehicular activities. Outside their portholes swim fish instead of satellites, but the psychological strain is the same. Close quarters, constant noise, and the knowledge that a single mistake could cost your life. These trials are not about pushing physical endurance alone. They are about conditioning the mind. Every astronaut must be able to think clearly when surrounded by chaos, to maintain focus when isolation and monotony threaten sanity. The ability to stay calm, logical, and compassionate under pressure can mean the difference between success and disaster. The training cycle is relentless and global. A candidate may spend 1 month in Russia mastering the Soyuz spacecraft, then another in Japan studying the Kibo laboratory, followed by weeks in Canada learning to operate the Canadarm2 robotic system. They become experts in systems designed by multiple nations, learning the engineering languages of each. Every button, every panel, every safety protocol must be memorized until it becomes second nature. And while astronauts are trained to face emergencies, they are also taught to appreciate the routine. On the International Space Station, the majority of work involves maintenance, scientific experiments, and daily checklists. Learning to find purpose in repetition, to perfect the small details, is essential. As one veteran astronaut observed, spaceflight isn't one long adventure. It's hundreds of small, carefully executed tasks. Behind every successful mission lies an invisible network of instructors, engineers, and mission controllers. They track every heartbeat, every data stream, ensuring that the astronauts are never truly alone. Trust is absolute between crew and ground, between nations, between individuals who may never meet but whose work determines survival. To train for space is to live a life suspended between two realities: the ordinary world of family, gravity, and air, and the extraordinary realm where none of those things exist. It's a world defined by preparation, where every second is accounted for, every risk anticipated. Yet, despite the regimentation, there is still room for wonder. When astronauts describe their training, their eyes light up not when speaking of procedures or drills, but of the moments when imagination meets purpose. The instant they realize that every screw tightened, every diagram studied, is part of a larger story. The story of leaving Earth, of standing on the threshold of the impossible, and stepping through. And for those who endure it all, the sleepless nights, the isolation, the endless travel, there comes a single day when the classroom disappears and the horizon changes. The next test will not take place underwater, underground, or in a simulator. It will unfold in the boundless silence above the world. Part 3. The final rehearsal. Preparing for launch. The final months before a mission are unlike any other period in an astronaut's life. After years of endurance training, technical preparation, and psychological testing, the transition from candidate to flight crew member begins. It is a strange mix of routine and anticipation. The calm before the storm, when every motion feels heavier, more deliberate, and every day edges closer to the moment when gravity will finally let go. The chosen few, a crew of perhaps 6, begin what is known as the flow to launch, a tightly choreographed series of rehearsals, simulations, and physical conditioning that will culminate in a journey beyond Earth's sky. Every week is mapped with precision. They spend one day in Houston reviewing life support procedures, another day in Star City mastering the Soyuz spacecraft, and the next in Cologne revisiting emergency operations for the European Columbus module. Training doesn't slow down, it intensifies. The focus narrows to specifics. The exact sequence of switch toggles during a depressurization, the precise motion required to stabilize a tumbling capsule, the scripted words to report a system anomaly in Russian or English. Nothing is left to chance. Every member of the crew must know the responsibilities of every other, able to assume any role at a moment's notice. In Houston, inside Building 9, the Cathedral of Mock-ups, the crew conducts integrated simulations that mirror real-life conditions on the International Space Station. These full crew rehearsals test communication, timing, and instinct. The astronauts are thrown into emergency after emergency. Fire, coolant leaks, loss of communication, power failure. They work as a single organism driven by reflex and trust. "You don't rise to the occasion," says one instructor. "You fall to the level of your training." At the same time, each astronaut undergoes intensive sessions at NASA's Johnson Space Center's Neutral Buoyancy Laboratory. These final EVA practices are 6-hour marathons beneath 6.2 million gallons of water. The suits are heavier now, their bodies leaner, their minds sharper. Every tether is checked, every maneuver rehearsed until it becomes muscle memory. The water blurs the boundary between simulation and reality. When they surface, blinking in the harsh fluorescent light, they are closer than ever to flight. The coordination between nations is immense. The Japanese Aerospace Exploration Agency, JAXA, trains them in operating the Kibo Laboratory, the most sophisticated experiment module on the ISS. In Canada, they learn the precision dance of the Canadarm2, a robotic limb capable of capturing and moving multi-ton spacecraft. At the European Astronaut Center, they revisit the Columbus module systems, mastering power grids, environmental controls, and communication arrays. Then comes the return to Russia, the cradle of human spaceflight. Star City, a place where history breathes through the walls, becomes home once again. Here, amid birch trees and aging concrete, astronauts practice every phase of the Soyuz launch and landing. The simulators creak with history. The instructors are veterans of 100 missions. Everything is conducted in Russian, commands, readouts, even jokes. Every astronaut learns the language not out of courtesy, but necessity. In space, communication can mean survival. Inside the Soyuz capsule simulator, the experience feels almost sacred. The cockpit is claustrophobic, 3 seats, walls lined with switches, blinking lights, and analog dials. Once the hatch seals, the world disappears. The commander and flight engineers practice launch sequences, engine burns, emergency separations, and ballistic re-entries. The centrifuge tests come next, spinning the astronauts at over 4 times the force of gravity. Muscle strain, vision tunnels, but they must remain alert, reading instruments and responding to alarms. Physical preparation merges with mental conditioning. The crew studies contingency plans for every scenario. Off-course landings in the Siberian tundra, ocean splashdowns, fires inside the capsule, or depressurization during orbit. They even rehearse survival drills in forests and frozen plains, learning to light fires, build shelters, and wait for rescue teams should their descent go awry. And then, as the final simulations end, something changes in the atmosphere. The laughter grows quieter. The smiles are still there, but softer, weighed with reflection. The crew begins their quarantine period, isolated from the outside world to prevent illness before launch. Family visits are brief and controlled. Communication with friends dwindles. Every day is devoted to preparation, briefings, and medical checks. In these quiet days, astronauts speak often of dreams, recurring visions of floating, of flying, of falling endlessly through the dark. They check their suits, their personal items, their mission patches. They record final messages for their families, just in case. And then they sleep, knowing that tomorrow the countdown will begin. Launch morning arrives like no other. The air is crisp at the Baikonur Cosmodrome in Kazakhstan. The Soyuz rocket, a spire of steel and fire, stands ready on its pad, surrounded by steam and floodlights. Crew buses arrive in silence. The astronauts wave to families and officials, their smiles calm but distant. The weight of years of preparation now compresses into minutes. Inside the suit-up facility, technicians help them into their Sokol suits, white and blue, pressurized, stiff. Every zipper, seal, and hose connection is checked 3 times. Heart monitors are attached, communications tested. The ritual is precise, almost ceremonial. One by one, they give the traditional salute, then step out into the freezing dawn. As the elevator rises along the rocket's side, the wind howls against the metal. They enter the capsule, strap in, and begin the pre-launch checklist. Voices fill their headsets, Russian, English, Japanese, the chorus of a global effort reaching its climax. The hatch seals. The countdown begins. In those final seconds, the crew feels the heartbeat of the rocket beneath them, a low vibration rising through their bodies. They hear the engines ignite, a deep, primal roar. The cabin trembles. The world outside fades to flame. And then, at the edge of the sky, as the engines thunder and the gravity of Earth loosens its grip, they cross an invisible line, 100 kilometers above the ground, and join the small fraternity of humans who have seen the planet from the outside. The impossible is no longer theory. It's real and it's happening now. Part 4. Life Beyond the Blue. Living on the International Space Station. The moment the engines shut down, silence takes hold. The first true silence most astronauts have ever known. Gravity, their lifelong companion, disappears. A pen floats from its clip. A glove drifts lazily past a visor. The world tilts, or perhaps the body does, and suddenly up and down no longer exist. For the first few minutes, the experience is both exhilarating and deeply disorienting. They've crossed the Kármán line. They are no longer of Earth. But the wonder of that moment quickly gives way to routine. Life aboard the International Space Station, the ISS, is less about drama than discipline. It's a world of constant hums, scheduled tasks, and a rhythm defined by sunrise and sunset every 90 minutes. 16 dawns and 16 nights in a single Earth day. For all its breathtaking beauty, space is an unforgiving workplace. The station itself is a floating city the size of a football field, assembled over decades by multiple nations. The modules bear the names of their makers: Zvezda and Zarya from Russia, Destiny from the United States, Kibo from Japan, Columbus from Europe. Each piece of the ISS represents a political miracle, a partnership between former rivals who once raced each other to the moon. Here, collaboration is survival. Daily life begins with a call from mission control, a calm voice in Houston, Moscow, or Tsukuba, reminding the crew of their schedule. Tasks are divided by minute. They calibrate instruments, conduct experiments, inspect air filters, replace water lines, and perform system checks. Every rotation of a valve, every button pressed, is documented and transmitted back to Earth. The data flow never stops. Even simple acts demand adaptation. Eating is a careful choreography of packets, Velcro, and patience. Water comes in floating spheres, captured and sipped before they drift away. Sleeping means strapping yourself into a cocoon so you don't float into a wall. A single misplaced object can become a hazard in zero gravity. A floating tool could puncture a panel or block an air vent. Still, amid the technicality, there is wonder. Looking out of the cupola, the panoramic observation window, astronauts witness a view that words can never fully describe. The blue curve of Earth wrapped in its fragile atmosphere, lightning storms flashing over continents, auroras shimmering at the poles like living curtains of light. The planet looks alive, breathing, impossibly beautiful. It's like looking at the soul of home, one astronaut whispered. And yet, that same beauty comes with a sense of fragility. From orbit, the atmosphere appears thinner than paper, a translucent shell that keeps every living thing alive. Many astronauts have said that seeing Earth from this perspective changes them forever. They call it the overview effect, a sudden awareness of the planet's unity and vulnerability. Borders disappear, politics fade. What remains is one world, one species, suspended in the void. But life aboard the station is not philosophical for long. The work continues, science never stops. More than 300 experiments are conducted during a typical 6-month mission. Studies on human physiology, material science, combustion, fluid behavior, and the effects of radiation on living cells. Each experiment, however small, is part of a vast network of inquiry that reaches from laboratories on Earth to the farthest reaches of physics. In one corner of the US module, an astronaut might be studying how protein crystals form in microgravity, research that could lead to breakthroughs in medicine. In another, a Japanese experiment tests the durability of new materials for deep space travel. In the European Columbus module, biological samples are exposed to cosmic radiation, simulating conditions on Mars. Maintenance never ends. Filters clog, valves leak, software glitches arise. Every malfunction is a puzzle that must be solved quickly and calmly. Astronauts become mechanics, electricians, plumbers, and scientists all at once. Sometimes they work 12-hour shifts, crawling through narrow tunnels of cables to replace a single circuit board. "You fix what breaks," said one veteran. "You don't have a choice. There's no hardware store in orbit. Communication with Earth is constant but limited by bandwidth and schedule. Video calls home are precious, voices delayed by seconds, laughter echoing through static. It's a strange kind of distance, close enough to see your loved ones' faces, but too far to touch them. When loneliness sets in, astronauts often turn to the window. The best therapy, one said, is watching a sunrise from space. Evenings aboard the ISS are quiet but never truly dark. Earth glows below like a lantern, and the stars above remain unblinking, unfiltered by atmosphere. Meals are shared, jokes exchanged in multiple languages, and music, often a guitar or a harmonica, fills the air. In those moments, the station feels almost human, a home above the world. Yet danger is never far away. Micrometeoroid warnings, pressure alarms, radiation spikes. The station is surrounded by threats invisible but constant. Every crew member knows that the nearest help is 400 kilometers below. If something goes wrong, there's only each other and the Soyuz capsule, their lifeboat back to Earth. Despite the risks, most astronauts describe their time in orbit as the most profound experience of their lives. Every day is a miracle, one said. Every orbit reminds you that you are both infinitely small and immeasurably lucky. Life on the ISS is not about escaping Earth. It's about understanding it, learning what it means to live together in fragile harmony, suspended between the blue below and the black beyond. It's a reminder that humanity's greatest experiment is not science, but coexistence. For now, this outpost in the sky is our frontier, but soon it will be our launching point. Because beyond the station, beyond low Earth orbit, lies a destination that has haunted human imagination for generations. Mars. Part 5. The machines that carry us. Rockets, risks, and the price of reaching space. Every astronaut knows one unspoken truth. Before you can explore space, you must first survive the journey there. The machine that carries them, a rocket, is both a masterpiece of engineering and a calculated gamble. Each launch is a controlled explosion, a fusion of science and audacity, where the margin between triumph and tragedy can be thinner than a human breath. From the first days of the space age, rockets were born from weapons. The same missiles that once threatened cities became the vehicles that carried humanity toward the stars. Engineers turned instruments of destruction into instruments of discovery. The technology didn't change overnight, only the purpose did. And yet, even now, the irony lingers. We reach for the heavens on pillars of fire forged for war. A modern rocket is a marvel of precision. Its engines must ignite in perfect sequence, its structure must withstand immense vibration and pressure, and its navigation must remain flawless even as it tears through the atmosphere at over 25,000 kilometers per hour. Every joint, every wire, every drop of fuel has been tested 1,000 times. But perfection is theoretical, and rockets, by nature, are unforgiving. At the Baikonur Cosmodrome, the Russian Soyuz rockets continue to fly, descendants of designs first drafted in the 1950s. They are elegant in their simplicity, refined through decades of experience. With more than 120 successful manned launches, the Soyuz remains the most reliable spacecraft in history. When an astronaut climbs into its capsule, they're not just trusting a machine, they're trusting 60 years of lessons written in fire. Other nations have developed their own launchers. Japan's H-2 rockets, India's GSLV, China's Long March, and Europe's Ariane 5 and Vega all contribute to the global effort to place satellites, cargo, and humans in orbit. Each carries its own philosophy. Some prioritize reusability, others payload capacity or environmental safety. The Russian Angara system, for example, is modular and designed to replace older, toxic-fueled models. The European Ariane 6 aims to cut launch costs by half. Progress in spaceflight is measured not just in distance, but in efficiency. But the most dramatic revolution has come not from governments, but from the private sector. When NASA turned its focus toward deep space exploration, commercial companies stepped in to handle low Earth orbit. The floodgates opened. SpaceX, Blue Origin, and a host of others began designing rockets that could not only reach orbit but come back. For decades, rockets were expendable. Single-use giants that fell into oceans or burned up in the atmosphere. SpaceX changed that. The Falcon 9, a sleek, two-stage rocket powered by reusable boosters, lands itself back on Earth minutes after launch. What once seemed impossible is now routine. Each successful landing marks a small but profound victory in humanity's effort to make space accessible. Reusability isn't just a technical achievement, it's an economic one. Every recovered booster reduces cost. Every recycled engine brings the dream of spaceflight closer to reality. But it also introduces new risks. Rockets must endure multiple flights without failure. Engineers study the scars of re-entry, refining materials, improving thermal protection, learning from every imperfection. In spaceflight, progress is always written in failure first. NASA's future lies in the Space Launch System, the most powerful rocket ever built, capable of sending astronauts to the Moon, Mars, and beyond. It stands taller than the Statue of Liberty, powered by engines once used on the Space Shuttle. Its purpose is not to reach orbit, but to escape it, to carry the Orion spacecraft and its crew toward deep space. Each test is a symphony of fire and mathematics, a reminder that even in the age of automation, rockets remain the ultimate expression of human ambition. But ambition comes with a price. For every successful launch, there are countless silent near misses, electrical anomalies, valve malfunctions, software errors caught just in time. And for every generation of astronauts, there are names etched into memorials. Challenger, Columbia, Soyuz 1, Soyuz 11. Space has no tolerance for mistakes. When something fails, it fails completely. Astronauts understand this better than anyone. During pre-flight briefings, they study every disaster, line by line, not as morbid history, but as survival training. They memorize what went wrong, how it happened, and how it could be prevented. It's not fear that drives them, it's respect. Respect for the engineers who build the rockets, for the controllers who monitor every heartbeat of the mission, and for those who lost their lives paving the way forward. Despite all the danger, the launch remains the most thrilling moment in human experience. As the engines ignite and the rocket tears free from the Earth, there is no sound like it. A thunder that shakes the bones, a vibration that passes through the chest and into the soul. The cabin trembles, every muscle tenses, every instinct screams to hold on. And then, in less than 10 minutes, the Earth falls away, replaced by the quiet infinite. It is in that moment that the line between technology and transcendence blurs. The rocket, the machine, the human, they become one. From chemical fire to digital precision, from disposable boosters to reusable spacecraft, our vehicles to the stars have evolved, but the essence remains unchanged. We still build them in the hope of going further, faster, safer. Every launch is a statement of faith in human ingenuity, and a reminder that exploration is never truly safe, only worthwhile. Soon, these machines will take us farther than ever before. The next destination is not just orbit or even the moon. It is a red world, far beyond the reach of home. And the countdown to that journey has already begun. Part 6. The Next Horizon. The mission to Mars for generations. Mars has been more than a planet. It has been a mirror, a reflection of humanity's imagination, fears, and deepest ambitions. From the canals imagined by 19th century astronomers to the dust storms captured by rovers today, the red planet has always hovered at the edge of the possible. And now, for the first time in history, someday has a date. NASA, ESA, Roscosmos, and a new wave of private companies all share the same vision: to send humans to Mars within our lifetime. The reasons are both scientific and symbolic. Mars is the only planet within reach that may once have harbored life, and might, in some hidden form, still do. It's a world that challenges us to prove not only that we can go there, but that we can stay. The journey, however, is unlike anything humankind has ever attempted. To reach Mars requires more than courage. It demands engineering on a scale never before achieved. The average distance between Earth and Mars is 225 million kilometers. Depending on orbital alignment, a one-way trip could take between 6 and 9 months. For the crew, that means living in a confined spacecraft for nearly 2 years, outbound, surface operations, and return combined, with no possibility of rescue. The mission design is still evolving, but the essentials are clear. Crews will likely travel aboard a modular spacecraft, a combination of propulsion units, habitat modules, and radiation shielding designed for deep spaceflight. NASA's Orion capsule will handle launch and re-entry, while the larger deep space habitat will provide living space en route. ESA contributes life support and propulsion systems, while SpaceX pushes forward with Starship, a fully reusable rocket designed to carry 100 tons of cargo or up to 100 people to the Martian surface. Mars isn't just a destination, it's a challenge written in physics. The planet's thin atmosphere, only 1% as dense as Earth's, makes landing a spacecraft exponentially harder. Parachutes barely work. Rockets must fire in perfect synchronization to slow descent. Even a small miscalculation in speed or angle could turn a billion-dollar craft into a crater. NASA's robotic landers have succeeded only through decades of trial and error, each one teaching engineers how to land larger and heavier payloads. But landing humans will require perfection. Then there's radiation, invisible, relentless, and lethal. Beyond Earth's magnetic shield, astronauts will be bombarded by cosmic rays and solar particles capable of damaging DNA and increasing cancer risk. Engineers are experimenting with hydrogen-rich materials, magnetic shielding, and water-filled walls to protect the crew. Some propose using Martian regolith, the planet's own soil, to cover habitats once they land. The same dust that makes Mars red could one day keep humans alive. Psychologically, the mission is as formidable as the engineering. The crew will experience complete isolation. No real-time contact with Earth. As messages take up to 22 minutes each way, there will be no emergency rescues, no quick returns. Every problem must be solved locally, every decision made with incomplete information. The mental resilience required rivals anything in human history. And yet, despite these risks, thousands have already volunteered. For them, Mars represents not danger, but destiny. "We've been explorers since the dawn of our species," says one astronaut candidate. Mars is simply the next logical step, the next mountain to climb. NASA's Artemis program, designed to return humans to the Moon, is the first stage of that journey. The Moon will serve as both testing ground and launching point, a place to practice long-duration missions, resource extraction, and surface construction under partial gravity. Technologies developed there, lunar habitats, in situ resource utilization, 3D printed structures, and closed-loop life support systems, will become the blueprint for Mars. Meanwhile, the robotic pioneers continue their silent work. Perseverance drills into Martian rock, storing samples that may one day be returned to Earth. The Ingenuity helicopter, the first aircraft on another world, scouts ahead like a mechanical scout for future explorers. Orbiters map potential landing sites rich in water ice, the key ingredient for both drinking water and rocket fuel. When humans finally arrive, they won't just be visitors. The goal is permanence, the establishment of a base capable of sustaining life without constant resupply from Earth. Solar arrays will power systems. Greenhouses will grow food. Water will be extracted from subsurface ice. The first Martian explorers will become settlers, engineers, and scientists all at once, caretakers of a fragile outpost on an alien world. But the journey to Mars is more than a technical challenge. It's a moral one. Should humanity spread to other worlds when we have yet to solve our problems here? Should we risk lives to reach a place so hostile, so barren, when Earth itself needs healing? These are the questions every space agency and every astronaut must confront. Perhaps the answer lies not in escape, but in perspective. Going to Mars won't save humanity, but it might remind us what we're capable of. It could reignite the collective imagination that once carried us from caves to cities, from sails to spacecraft. Could prove that even in an age of division, nations can still unite for something greater than themselves. For now, Mars remains a red light in the night sky, tantalizing, distant, silent. But the first footprints are coming. The technology exists, the will is gathering, and the countdown, though long, has already begun. When that first crew departs Earth orbit, humanity will cross another threshold. Not just between planets, but between eras. The age of interplanetary life will have begun. Part 7. Science in the Void, experiments that change Earth. Space exploration has always carried a paradox. The farther we travel from Earth, the more we learn about it. The International Space Station, orbiting 400 kilometers above the planet's surface, isn't just a symbol of exploration. It's a laboratory where gravity, time, and matter behave in ways impossible to reproduce on the ground. In that silent environment, free of atmospheric interference and the constant pull of weight, scientists conduct experiments that reshape medicine, technology, and our understanding of life itself. The ISS is, in many ways, humanity's greatest scientific collaboration. Over 3,000 experiments from more than 100 countries have been performed there. The results have led to breakthroughs in genetics, material science, environmental monitoring, and even climate research. It is a platform that unites physicists, biologists, chemists, engineers, and doctors, all working toward the same goal: to use the vantage point of space to improve life on Earth. Microgravity, the near-weightless state that defines orbital existence, transforms the behavior of matter. Liquids float in perfect spheres. Flames burn in blue globes instead of flickering tongues. Crystals grow larger, purer, and more uniform. In this environment, researchers can observe processes normally distorted by gravity. Protein crystallization, for instance, behaves differently in space, allowing scientists to develop more accurate models of complex molecules. This data helps in designing new drugs to treat diseases such as Alzheimer's, Parkinson's, and certain cancers. The lessons learned in orbit also extend to human biology. Living in space alters the body in fundamental ways. Bones lose density, muscles weaken, and fluids shift toward the head, affecting vision and pressure in the brain. To counter these effects, astronauts exercise up to 2 hours a day using specialized treadmills, resistance machines, and stationary bicycles. Each session is an experiment in maintaining the human form in an environment evolution never prepared it for. The data gathered informs treatments for osteoporosis, circulatory disorders, and long-term immobilization on Earth. Even the smallest tasks aboard the station, growing plants, recycling water, monitoring microbes, yield insights vital for future missions. The veggie experiment, for example, demonstrated that fresh vegetables can grow in microgravity using LED light and minimal soil, a key step toward self-sufficiency on Mars. Another study tested how bacteria adapt to radiation and confined environments, providing data to develop stronger antibiotics and sterilization systems. Beyond biology, the ISS serves as a front-row seat to the planet itself. Orbiting the Earth every 90 minutes, the crew witnesses the planet in constant motion. Hurricanes forming, wildfires spreading, ice caps shifting. High-resolution cameras and spectrometers mounted on the station capture these phenomena, giving scientists unparalleled tools to study climate change. Data from space has helped track deforestation, pollution, and coral bleaching in real time, revealing how interconnected Earth systems truly are. The vantage point also enables technology testing. Materials exposed to the vacuum of space undergo degradation that would take decades on Earth. Engineers use these results to design more durable alloys, coatings, and composites for satellites, aircraft, and even bridges. The MISS Materials International Space Station experiment arrays have hosted over 4,000 samples, from solar panels to paints, helping scientists understand how radiation, temperature extremes, and micrometeoroids affect materials. Physics, too, finds a new frontier in orbit. The Cold Atom Lab aboard the ISS creates temperatures just above absolute zero, allowing researchers to study quantum phenomena in ways impossible under gravity. Particles can be trapped and manipulated for longer durations, helping physicists explore questions at the intersection of relativity and quantum mechanics, the foundations of future technologies like quantum communication and computing. But perhaps the most profound lessons are those of collaboration. No single nation owns the ISS. It is shared, maintained, and operated by many. Russian modules dock beside American laboratories. European experiments rely on Japanese hardware, and communication loops circle the globe. Every successful experiment represents the collective effort of thousands of people. Engineers in Houston, scientists in Cologne, flight controllers in Moscow, technicians in Tsukuba, all synchronized across time zones and languages. It's easy to forget, amid the hum of pumps and the glow of monitors, that every screw, every circuit, and every ounce of air aboard the ISS came from Earth. The station is both a triumph and a reminder. Humanity's greatest achievements are built on interdependence. And while its discoveries shape our world, the ISS is also preparing us for the next one. The technologies perfected here, closed-loop life support, efficient recycling, autonomous systems, will form the backbone of lunar bases and Mars habitats. Every experiment is a rehearsal for survival beyond Earth. In the end, the science of space is not just about learning new facts. It's about redefining the possible. When an astronaut gazes out of the cupola after finishing an experiment, they're looking not just at Earth's horizon but at humanity's, a boundary that expands with every question we dare to ask. The station orbits on, circling Earth 16 times a day, each pass a symbol of human persistence and curiosity. But even as it continues to reveal the secrets of nature, another generation of scientists is looking farther, to the next laboratory, not in orbit but on another world. The stage is shifting. The next great experiment will not be above Earth but on it, or rather on the red sands of a neighboring planet. Part 8. The fragile body. How space changes the human being in space. Everything we take for granted on Earth, air, gravity, warmth, pressure, disappears. The human body, a masterpiece of terrestrial evolution, is suddenly misplaced. It was never designed to float, to drift, or to endure the deep silence of the cosmos. And yet, in the last few decades, we have forced it to adapt. We've learned that to live beyond Earth is not just an engineering challenge. It is a biological experiment. From the moment astronauts leave the planet, their bodies begin to change. Blood and other fluids, no longer pulled downward by gravity, rush toward the head. Faces puff up, legs thin, and sinuses clog. It's an effect known as fluid shift, and it alters everything from vision to balance. Within days, some astronauts develop a condition known as space adaptation syndrome, essentially cosmic motion sickness. Nausea, dizziness, headaches. The brain, confused by the lack of up and down, struggles to reconcile what the eyes see with what the inner ear feels. Over time, deeper changes set in. Without gravity's constant pull, bones begin to weaken. Calcium leaches into the bloodstream, and astronauts can lose up to 1% of bone density per month, a rate that would cripple most humans on Earth. Muscles, too, atrophy rapidly, especially those used for posture and walking. The heart, no longer working against gravity to pump blood upward, becomes slightly rounder, weaker. Even the immune system begins to misfire. The solution, paradoxically, is to make space harder. Astronauts aboard the International Space Station spend 2 to 3 hours every day exercising, running on treadmills strapped down by bungee cords, cycling against resistance, lifting vacuum-based weights. The goal is not fitness, but preservation, to trick the body into remembering gravity. These workouts maintain cardiovascular strength, bone density, and muscle tone, turning each astronaut into both explorer and test subject. Diet is equally critical. Food in orbit isn't just fuel, it's chemistry. Menus are calibrated to balance calcium, potassium, and sodium to counteract bone loss and fluid retention. Hydration must be meticulously managed. Even thirst behaves differently when fluids don't settle in the body as they do on Earth. Astronauts learn to listen to cues their bodies no longer send, to drink not when they feel thirsty, but when the schedule says so. Then there's radiation. Outside Earth's protective magnetosphere, cosmic rays bombard every cell. Over months, this invisible onslaught can damage DNA, increase cancer risk, and accelerate aging. The ISS is shielded by its low orbit and structure, but future deep space missions will face exposure far beyond safe limits. Engineers are studying layered shielding, water tanks, polyethylene walls, and even magnetic fields to guard against the unseen storm. Still, perhaps the most profound effects of spaceflight are not physical but psychological. The human mind was shaped by open skies, green landscapes, and the rhythms of sunrise and sunset. In orbit, all of that vanishes. The station hums with machinery. The light cycles every 90 minutes. There is no weather, no scent, no true silence. Over time, this deprivation changes perception. Astronauts report vivid dreams, emotional highs and lows, and an almost spiritual awareness of time. Isolation compounds the strain. A 6-month mission on the ISS means living in a metal tube the size of a bus with 5 other people, no privacy, no escape. Every word, every gesture matters. Minor irritations can grow into deep resentment if not managed. That's why psychological training is as essential as engineering. Astronauts learn active listening, conflict resolution, empathy. In a sense, space teaches humanity in its purest form, survival through understanding. The connection to Earth becomes both lifeline and torment. Families send recorded messages. Mission Control offers daily briefings, but real-time contact is fleeting. Some astronauts keep journals. Others paint, write music, or watch the planet pass below in silence. For many, that view of Earth, luminous and whole, becomes an anchor. "You look down," said astronaut Nicole Stott, "and you realize you're not just floating above the world, you're part of it. You always have been." After months in orbit, returning to Earth is as strange as leaving it. Gravity reasserts itself with cruel force. Legs feel heavy, muscles tremble, inner ears rebel. Many astronauts faint after landing. Some describe the first steps on solid ground as walking through sand. The rehabilitation process can take months, learning again how to balance, how to walk, how to trust the body that once defied gravity. And yet, despite the hardships, nearly all say the experience changes them for the better. Their perception of time, of scale, of life itself shifts. They return more patient, more aware, more connected. Space strips away the noise of daily existence and leaves behind only essentials: breath, motion, purpose. Scientists call this body of research space physiology, but astronauts often call it something else: humility, because in the vastness of the cosmos, they see their own fragility made visible. The body is resilient but temporary, finite yet adaptable. And that realization that we can change, survive, evolve, may be the most important discovery of all. It tells us that humanity is not bound to one world, that life itself can learn to bloom anywhere, even in the void. The next step, then, is not just to endure space, but to thrive in it, to build a life where gravity is optional and distance no longer divides. And to do that, we must first ask, if space can change the body so completely, what will it do to our sense of being human? Part 9. Echoes from Earth, Global Reactions to the New Space Age. While astronauts float above the world in silence, Earth itself hums with noise, political debates, scientific conferences, viral headlines, and public fascination. Each mission, each rocket launch, sends ripples through a planet still divided by borders but united, if only briefly, by wonder. The space age never truly ended. It evolved. And in this new century, it has become not just a scientific pursuit, but a mirror reflecting humanity's hopes, fears, and competing visions of the future. Every launch draws eyes skyward. When the engines ignite and the plume of fire rises through the atmosphere, millions pause, in living rooms, on phone screens, at schools and cafes. For a moment, the divisions of nations blur, replaced by a single collective gaze. Spaceflight, once the domain of Cold War rivalry, has become a shared human ritual, one that transcends politics, even as it is shaped by it. But beneath the poetry of exploration lies a network of power, ambition, and ideology. Governments and private companies alike recognize that control of the skies means influence over the future. Satellites monitor borders, map resources, and connect economies. Rockets capable of launching payloads into orbit can just as easily launch weapons. The frontier of space is both a laboratory and a battlefield, a paradox humanity has yet to resolve. In recent years, the landscape of exploration has shifted dramatically. No longer dominated by the United States and Russia, it now includes a constellation of new players. China's Tiangong space station orbits independently, symbolizing the nation's growing confidence and technological mastery. India's Chandrayaan-3 mission landed near the moon's south pole, a feat once thought possible only for superpowers. Meanwhile, the United Arab Emirates sent HOPE, its own probe, to Mars, the first from the Arab world. Europe, for its part, continues to bridge alliances through the European Space Agency. Its astronauts, trained in Cologne and Moscow alike, represent cooperation over competition. "When you're in orbit," said ESA astronaut Samantha Cristoforetti, "you don't see borders. You see one planet." The rest is invention. Yet, even in that idealism, earthbound realities persist: budgets, politics, rivalries. The balance between unity and ambition remains delicate. Private industry has added a new dimension. SpaceX, Blue Origin, Rocket Lab, and others are redefining what it means to explore. What was once government territory has become an emerging marketplace. Space tourism, once a fantasy, is now a headline. Civilians have orbited Earth, paying fortunes for minutes of weightlessness. Critics call it spectacle for the wealthy. Supporters call it the democratization of the cosmos. Both may be right. Social media has amplified this fascination. Every launch is live-streamed, every astronaut's post from orbit shared with millions. The voice of science has never reached so far or so fast. A single photograph of Earth, a fragile blue sphere rising over the lunar horizon, can reignite global reflection. Yet, the digital age has also blurred the line between awe and noise. Conspiracy theories and misinformation thrive alongside genuine curiosity. The stars have never been closer, yet understanding them has never been more complicated. Meanwhile, art and culture have absorbed the imagery of the new space age. Painters, filmmakers, musicians, and writers reinterpret the silence of space as metaphor for isolation, for hope, for the search for meaning in a crowded world. The cosmos has become both a destination and a canvas. In music, orchestras echo rocket launches. In fashion, metallic tones and futuristic designs mimic astronaut suits. Even philosophy feels its influence. The question of what it means to be human when we live beyond Earth has entered classrooms and pulpits alike. Economically, the shift is monumental. The global space industry, once a specialized sector, now drives telecommunications, navigation, weather forecasting, and climate monitoring. A single satellite launch can connect millions or disrupt entire markets. Nations without launch sites now invest in satellite networks, building new dependencies that cross continents. Space has become the invisible infrastructure of modern civilization. But there's also a growing unease. Environmentalists warn of orbital debris, the space junk that threatens to turn low Earth orbit into a minefield of shattered metal. Scientists caution that unchecked launches could one day trap us under a shell of debris, making spaceflight too dangerous to continue. Others fear the militarization of space, the quiet testing of anti-satellite weapons, the weaponization of data, the possibility that the final frontier may become the next arena of conflict. And yet, amid the complexity, a deeper truth persists. Space exploration still inspires. Children draw rockets in classrooms. Universities fill with new engineers. Documentaries trend, books sell, and nations collaborate. Even cynics find themselves pausing when a spacecraft lands on another world and sends back a single image of a dusty horizon under an alien sun. The echoes of space travel are everywhere, in science, politics, art, and identity. The act of reaching outward forces humanity to look inward. We see our fragility, our ingenuity, our contradictions. Space is not an escape from Earth, but a reflection of it. A stage upon which we replay the same dramas, but also a place where we might finally learn to transcend them. And as humanity prepares to set foot on Mars, these echoes will only grow louder. The question is no longer can we go, but should we? And how will doing so redefine what it means to be human, to belong, to dream? The next part of the story looks not outward, but inward, toward the people who dedicate their lives to building humanity's bridge to the stars. Engineers, scientists, doctors, and dreamers, the quiet heroes behind every launch. Because in the end, no one goes to space alone. Part 10. The engineers of tomorrow, minds that build the future. Every launch, every mission, every photograph of a distant world begins the same way, with a mind at work. Long before the countdown, before astronauts climb into their capsules, the engineers, scientists, and technicians of Earth are already there, building, calculating, and imagining what has never been done before. If astronauts are the visible face of exploration, these people are its heartbeat. Quiet, precise, relentless. To build for space is to live in a world where failure is not an option, and yet it is constant. Every screw, every circuit, every thermal seal must survive extremes that no laboratory can perfectly replicate. Temperatures that swing from searing heat to cryogenic cold. Radiation that eats through metal. Vacuums that turn air into nothing. There is no margin, no forgiveness. You don't build for comfort, one NASA engineer once said. You build for survival. The path to becoming such an engineer is as demanding as the missions themselves. It begins with curiosity, a fascination with how things work, and matures through years of study and sacrifice. The next generation learns to think in numbers, to dream in equations, to translate imagination into machinery. They study physics, aerodynamics, robotics, material science, and systems engineering. But beyond the degrees and credentials lies something deeper, the ability to see failure not as defeat, but as information. In clean rooms and hangars across the world, in Houston, Cologne, Tokyo, Bremen, and Bangalore, thousands of specialists labor over spacecraft parts the size of thumbnails and rockets taller than cathedrals. They wear white suits to prevent contamination, and every movement is deliberate. One misplaced fingerprint could cost millions. One loose wire could doom a mission. The process is slow, repetitive, and exacting, but within that precision lies poetry. Behind the hum of computers and the whir of robotic arms is a culture of collaboration unlike any other. Engineers from different nations, languages, and ideologies work side by side, united by the simple truth that physics has no borders. The European Space Agency's laboratories in Germany routinely coordinate with NASA's Johnson Space Center, while Japan's Tsukuba facility sends components to Kazakhstan for integration on Russian rockets. It's a choreography of trust and of shared ambition. Some focus on propulsion, harnessing controlled explosions powerful enough to lift hundreds of tons off the ground. Others work on guidance systems, ensuring that a spacecraft traveling 300 million kilometers will arrive within a few meters of its target. Still others design the habitats where astronauts will live, combining ergonomics, biology, and psychology to create comfort in a place that has none. Among them are the new pioneers of sustainability, engineers who seek not only to reach space but to protect Earth in the process. They design reusable rockets, lightweight solar panels, and low-emission fuels. They track orbital debris and plan systems for space recycling. Their goal is not conquest, but coexistence, to ensure that the sky remains open for generations to come. And then there are the dreamers, the visionaries who look not at the next mission, but at the next century. They are building concepts for nuclear-powered spacecraft, ion drives that accelerate for months without refueling, and habitats that could orbit Mars or Jupiter's moons. To them, space is not a destination but a continuum. Each innovation is a stepping stone toward a civilization that spans worlds. Yet, for all the grandeur of their work, most engineers describe their jobs in humble terms. They rarely see the launches in person. Many never meet the astronauts who rely on their designs. They live in a cycle of prototypes, revisions, and tests that stretch over years. When something fails, they start again. When something succeeds, it is celebrated quietly, with a nod, a handshake, and a return to work. It's a life of invisible victories. When a rover lands on Mars and sends its first image home, thousands of unseen hands are behind that pixel. When a solar array deploys perfectly, or a robotic arm captures a cargo ship in orbit, it's not just luck. It's the sum of human persistence. The engineers of tomorrow inherit that legacy. A culture that believes that progress, no matter how small, is worth the risk. As the next era of exploration unfolds, with lunar bases, Martian colonies, and interplanetary travel, their role becomes even more vital. They must solve problems we can barely define. How do you build machines that last decades in radiation? How do you grow food on barren soil? How do you protect humans from the emptiness between planets? The answers will not come easily. They will emerge from the quiet brilliance of thousands of minds working in parallel, each solving a single piece of an infinite puzzle. Together, they are building the framework of a new civilization, one where the term Earth-made becomes a mark of pride, not limitation. When future historians write the story of humanity's expansion into space, they may remember the first footprints on Mars or the first colony on the Moon. But beneath those milestones will lie the work of countless engineers, men and women who never left Earth, but who gave humanity the tools to leave it behind. They are the bridge between imagination and reality, the keepers of flame and formula, the ones who turn equations into dreams and dreams into engines. And though they stand firmly on the ground, their work ensures that the rest of us can touch the stars. Part 11. The politics of the infinite power, cooperation, and the new space race. In the early years of space exploration, the cosmos was a battlefield. Two superpowers, the United States and the Soviet Union, raced to prove not just scientific supremacy, but ideological dominance. Every orbit, every flag planted, every photograph from the Moon carried political weight. The space race of the 20th century was not merely a contest of rockets. It was a demonstration of will, economy, and power. Half a century later, the race has returned, but its rules have changed. Today's space age is no longer bipolar. It is multipolar, crowded, and complex. More than 80 nations operate satellites. Dozens maintain active launch programs. Private corporations wield influence once reserved for governments. The frontier that once symbolized unity and curiosity now reflects the world's tangled web of ambition. For all its grandeur, space has always been political. Every mission, every partnership, is shaped by diplomacy and funding as much as engineering. The International Space Station stands as humanity's most successful experiment in cooperation, built by 15 nations, sustained by treaties that outlasted the Cold War. American and Russian astronauts share meals, jokes, and experiments in orbit, even when their governments argue below. It is a fragile peace, floating above geopolitics. Yet even that peace is not guaranteed. In recent years, shifting alliances and economic pressures have tested the balance. Russia has announced plans to build its own orbital station, while NASA pivots toward partnerships with commercial companies and international allies for the Lunar Gateway, a new outpost designed to orbit the Moon. China, excluded from the ISS, constructed its own Tiangong. Once a solitary dream, it is now fully operational, with modular design and growing international participation. The result is a quiet competition, a race not to conquer space, but to define its future governance. Who owns the Moon's resources? Who sets the rules for Mars? Who has the right to mine asteroids or to deploy massive satellite constellations that fill the night sky with artificial stars? The Outer Space Treaty of 1967, drafted in the shadow of the Apollo missions, declares space as the province of all humankind. But in the age of private enterprise, that principle is being tested. Companies like SpaceX, Blue Origin, and Planetary Resources push boundaries once controlled by nations. Their ambitions, reusable rockets, asteroid mining, global internet networks, blur the line between exploration and exploitation. Supporters argue that innovation thrives when competition is unleashed. Critics warn that without regulation, the cosmos could become a new Wild West. The question is no longer whether humans can reach other worlds, but whether they can do so responsibly. Meanwhile, satellites have become the nervous system of civilization. They guide airplanes, enable communication, monitor weather, and provide navigation for billions. But they also serve as tools of surveillance and warfare. Anti-satellite missile tests, conducted by multiple nations, have littered orbit with dangerous debris. Each fragment, traveling at 27,000 kilometers per hour, can destroy another satellite or puncture a spacecraft. Space warfare, once science fiction, is now a matter of strategy briefings and defense budgets. Despite the tensions, cooperation endures, often quietly, beneath the headlines. Data from Earth observation satellites is shared globally to track wildfires, crop yields, and climate change. International rescue agreements ensure that any astronaut in distress, regardless of nationality, will be aided by others. When a Japanese cargo ship docks with the ISS, Canadian robotics guided in. When a Russian module malfunctions, American controllers help troubleshoot it. Humanity's best instincts persist, even in orbit. And beyond politics, there is the symbolism. Space remains a mirror of national pride. When India landed Chandrayaan-3 near the moon's south pole, millions celebrated not only a scientific milestone but a statement. We belong here too. When the UAE sent its first astronaut into space, Arab children saw themselves reflected in the visor of a spacesuit. Each mission, no matter how small, expands the idea of who belongs in space. Yet, as nations rise and compete, a deeper philosophy is taking hold, that space, unlike land or sea, cannot be owned, only shared. It is a commons, fragile and vast, demanding stewardship rather than conquest. The Artemis Accords, signed by over 24 countries, attempt to enshrine that ideal: transparency, mutual aid, and the peaceful use of outer space. Whether these agreements hold will determine the moral tone of the next century. In many ways, the politics of space mirror those of Earth. Alliances formed, rivalries reignited, power consolidated. But the stakes are higher. For the first time, our actions beyond Earth have consequences that could echo across generations. A conflict in orbit could cripple global communications. A mismanaged resource race could poison the dream of exploration. The cosmos is not infinite in its capacity for human mistakes. Still, hope persists. Scientists, diplomats, and explorers continue to argue, collaborate, and create, all under the same shared night sky. They understand that humanity's survival, both physical and moral, may depend on whether we can learn to cooperate in the one place where division makes no sense: the vacuum between stars. The politics of the infinite are still unfolding. Power struggles will come and go, treaties will be rewritten, and corporations will rise and fall. But the deeper question remains unchanged. Can we carry our best selves into space, or will we bring our worst? As the next chapter of exploration begins, with Mars missions, lunar settlements, and the first whispers of interstellar travel, the answer will shape not just our future, but our definition of what it means to be a civilization. Part 12. Signals from the future, breakthroughs, leaks, and the edge of discovery. Every generation believes it stands at the edge of understanding, that it has finally seen far enough into the unknown to grasp what lies beyond. Yet every time we reach that edge, it moves just out of sight, just beyond the next orbit, the next experiment, the next faint signal across the void. In space exploration, progress is measured not only by what we know, but by what we have begun to suspect. The 21st century has delivered more discoveries than the first 50 years of spaceflight combined. Telescopes like James Webb and Euclid now peer billions of light years into the past, capturing galaxies formed before Earth itself existed. The Voyager probes, launched decades ago, continue to send whispers from interstellar space, faint radio pulses crossing the emptiness between stars, reminding us that our machines have already gone where our bodies cannot. And yet, amid these triumphs, another story unfolds, one more mysterious, more human. Data leaks, unexplained observations, unconfirmed transmissions. Scientists and enthusiasts alike argue over what they might mean. Are they simply errors in instrumentation, or glimpses of something greater? In 2027, an unusual narrowband signal was detected by a radio telescope in Australia's desert. It originated near Proxima Centauri, the closest star to our own, but its pattern did not match any known natural phenomenon. For weeks, speculation grew. Was it interference, cosmic coincidence, or something else entirely? The official explanation, months later, attributed it to terrestrial contamination. But in private, several researchers admitted that the data remained anomalous. Events like this reveal how fragile the boundary is between science and myth. Every strange reading, every flicker of light, reawakens the oldest question of all. Are we alone? Governments tread carefully. For every confirmed anomaly, there are hundreds of classified reports, atmospheric phenomena, unidentified orbital objects, unexplained sensor readings. Most are eventually dismissed. Some are not. Leaks from within space agencies and defense departments often ignite public fascination. Documents reference non-terrestrial materials, sensor anomalies, unexplained high-altitude events. The wording is deliberately cautious, neither confirmation nor denial. Scientists urge restraint, reminding the public that extraordinary claims require extraordinary evidence. Yet the hunger for discovery is difficult to contain. In the age of instant communication, mystery travels faster than truth. Meanwhile, the frontier of discovery expands on multiple fronts. In laboratories on Earth, quantum communication experiments test the limits of entanglement, the ability to transmit information instantaneously across any distance. In orbit, experimental satellites use laser links to achieve speeds once thought impossible. The dream of a unified space internet, one that connects every probe, station, and colony in real time, edges closer to reality. Elsewhere, artificial intelligence has begun to play a silent but transformative role. Autonomous systems now navigate spacecraft, analyze data, and even identify patterns in deep space signals that human eyes might miss. AI algorithms process terabytes of telescope imagery, spotting anomalies, distant planets, transient flares, or unknown spectra, before scientists can even review them. In many ways, machines have become our first explorers, venturing into realms we cannot yet reach. Some discoveries, however, come by accident. In 2031, an ESA probe studying cosmic background radiation recorded a repeating infrared pulse from the outer solar system. The pattern was precise, rhythmic, not noise, not cosmic rays. The signal vanished after 72 hours, never to return. Officially, it was a hardware malfunction. Unofficially, it remains one of the most debated mysteries in modern astronomy. Even without such enigmas, the data pouring in from across the solar system is staggering. Ice plumes erupting from Saturn's moon Enceladus contain organic molecules. Subsurface lakes on Mars show traces of saline water. Europa's surface hides an ocean deeper than Earth's. The probability of life, microbial, alien, ancient, grows less theoretical by the day. The more we look, the more the universe seems unwilling to be empty. But these revelations also raise deeper, more uncomfortable questions. If life exists elsewhere, what will it mean for religion, for philosophy, for the story humanity tells about itself? If we discover intelligence beyond Earth, will we be ready, politically, psychologically, spiritually, to accept it? Some scientists argue that contact, if it ever happens, will come not from a message but from a mirror, from understanding that we, too, are cosmic organisms shaped by chance and physics. Others believe the universe has been whispering all along, in the language of mathematics, radiation, and gravity, and that we simply haven't yet learned to listen. For now, the signals continue. Faint, sporadic, sometimes explainable, sometimes not. The search for meaning goes on, blending science and wonder into a single pursuit. Each experiment, each anomaly, each unanswered question is a reminder that exploration is not about finding closure, but about embracing mystery. The edge of discovery is not a line but a horizon, one that recedes every time we reach it. Humanity has stepped beyond the Earth, touched the moon, and built homes in orbit. Soon it will walk on Mars. But beyond every achievement lies the same silence, vast and waiting. Perhaps the universe does not need to answer us. Perhaps the message is the journey itself, the act of listening, of reaching, of wondering. And still, the antennas turn skyward, scanning the black. Because one day, that silence may speak back. Part 13, The New Frontier, Colonies, Conflicts, and the Birth of a Multi-Planet Species. The idea of a human colony beyond Earth once belonged to the realm of fiction. A dream painted in pulp magazines and film reels, a symbol of boundless optimism. Yet now, in the middle of the 21st century, what was fantasy has begun to take form in steel, silicon, and soil. The first generation of off-world settlers is already being selected. Contracts are signed, habitats tested, and flight manifests drawn up. humanity stands at the threshold of becoming a multi-planet species. Mars is the first target. The red planet, cold, airless, and unforgiving, is paradoxically our most hospitable neighbor. Its 24-hour day, polar ice, and sunlight make it the logical outpost. The earliest missions will resemble research stations more than cities. Compact modules linked by tunnels, each containing laboratories, hydroponic farms, and life support systems. Every kilogram of material will be precious, every breath recycled. NASA's Artemis Gateway program and SpaceX's Starship missions converge on the same goal: permanent human presence. The first settlers will arrive in small crews, scientists, engineers, biologists, armed with machinery to produce oxygen, extract water from the soil, and generate power from sunlight. Each success will multiply survival odds. Each failure could end the colony. The margin for error will be measured not in meters, but in heartbeats. Other players are joining fast. China's Tianwen program plans its own Mars base within 2 decades. Europe's Aurora initiative envisions a network of autonomous habitats built through 3D printing with local regolith. Private consortia, flush with investor optimism, design modular habitats and robotic mining rigs to harvest iron, nickel, and water ice. The frontier has become a marketplace, not of gold, but of data, energy, and opportunity. And wherever there are frontiers, there are conflicts. Legal scholars and diplomats now grapple with questions that once seemed hypothetical. Who owns the resources of Mars? Can a company claim a crater or a valley? The Outer Space Treaty forbids national sovereignty beyond Earth, yet it says nothing of private enterprise. The new settlers will live under Earth's laws, but which ones? American, Chinese, European? What happens when communication delays make command from Earth impossible? For those first crews, authority will be practical, not political. Survival will depend on cooperation more than ideology. In the sealed corridors of a Martian base, every argument about territory or faith will yield to the hum of air filters and the need to share oxygen. Conflict will exist, but so will an understanding that division is death. In that sense, Mars may teach humanity what Earth has long forgotten. The colonists themselves will face a transformation deeper than politics. Generations born away from Earth will grow under weaker gravity, altered radiation, and a different sky. Their bodies may adapt: taller frames, weaker bones, new circadian rhythms. Their languages and cultures will evolve in isolation. Over centuries, the children of Mars may no longer call themselves Earthlings at all. They will be Martians, heirs to a new environment and a new identity. Technology will shape this transition. Advances in bioengineering may protect future colonists from radiation or help them process nutrients scarce in Martian soil. Robotics will handle the most dangerous tasks: mining, construction, exploration, guided by artificial intelligences that learn from each decision. Energy will flow from nuclear microreactors and vast solar arrays. Greenhouses will turn carbon dioxide into oxygen and food. In time, domes of transparent polymers may rise over valleys, and humans will walk outside not in bulky suits but under breathable air, an act of audacity called terraforming. Yet, even as optimism grows, so too does caution. Scientists warn that altering another planet could erase clues about its past life or ecological potential. Ethicists debate whether humanity has the right to reshape a world before fully understanding it. Others worry that our flaws, greed, inequality, nationalism, will follow us outward, carried like seeds across the void. The challenge is not just to survive elsewhere, but to become something better there. Still, the idea is irresistible. Colonies represent more than expansion. They are a kind of insurance, a safeguard against extinction. A meteor impact, a viral catastrophe, a global war, any could erase civilization on Earth. To exist on 2 worlds is to ensure that our story continues. Elon Musk once called it life's great filter test. Scientists prefer a simpler phrase: planetary redundancy. For now, the first colonies remain plans on paper and prototypes in deserts. But the momentum is unmistakable. Every successful test flight, every robotic cargo drop, every simulation in Antarctica brings the future closer. The distance between Earth and Mars may be measured in millions of kilometers, but the distance between imagination and reality has never been smaller. When the first settlers step onto the red dust, they will not just plant a flag. They will plant continuity, proof that life can move outward, that humanity can transform challenge into creation. They will look up and see Earth, a pale blue point in the pink sky, and know that for the first time in history, home has more than one address. The birth of a multi-planet species will not happen in an instant. It will unfold slowly, one module, one breath, one sunrise at a time. But once begun, it may never stop. From Mars to the moons of Jupiter, to the icy oceans of Europa, the horizon will stretch endlessly forward. And with that expansion will come a new question, not where we can go, but who we will become once we get there. Part 14. The Long Silence. Lessons from the Void and the Meaning of Home. In the stillness of space, silence is not emptiness. It is presence. The hum of the spacecraft, the faint vibration of life support systems, the quiet breath inside a helmet. These are the only sounds between humanity and infinity. For astronauts and settlers alike, this silence becomes both companion and teacher. It reminds them of where they came from and what they left behind. As humanity begins to stretch its reach across the solar system, the notion of home becomes more complex. Once, it meant a country, a city, a house, a set of coordinates on a single blue planet. But for those who live and work beyond Earth, home is no longer a place. It is an idea, fragile, portable, reconstructed with every heartbeat. In the darkness between worlds, isolation is absolute. Radio signals crawl through space at the speed of light, yet even that feels too slow. A message from Mars takes nearly 20 minutes to reach Earth. A question asked in the morning may not be answered until evening. In that gap of silence, people rediscover patience and reflection. The first Martian settlers will live with that delay like a second heartbeat. Conversations with loved ones will be fragmented, letters instead of voices, memories instead of presence. A mother may see her child's face only through grainy recordings. A scientist may share a discovery with colleagues weeks after it happens. Time itself will lose its symmetry. But in that distance, something profound will grow. The settlers will find new ways to connect, through art, ritual, and shared purpose. They will build communities not defined by geography, but by intention. Music, poetry, and laughter will fill the airlocks and tunnels, reclaiming the silence as something human. They will learn that meaning does not depend on proximity, but on care. The silence also changes perception. Away from Earth's noise, the mind begins to hear other rhythms. The pulse of machinery, the shifting of dust, the whisper of air moving through ducts. Many astronauts describe an almost meditative clarity in orbit, a heightened awareness of small details. On Mars, that clarity may deepen into something spiritual, an awareness of being alive in a universe that seems indifferent, yet allows life to exist at all. For all our technology, we are still creatures of habit, emotion, and longing. The settlers will carry pieces of Earth with them, soil sealed in glass, family photographs, recordings of rain and birdsong. These small tokens will anchor them against the vast unknown. They will remind them that exploration is not escape, but extension, an act of faith in continuity. Back on Earth, the silence of space echoes in unexpected ways. The sight of human lights glowing on another world will change how we see ourselves. Boundaries between nations will seem smaller. Conflicts may look trivial when compared to the effort required to sustain life in a hostile sky. For the first time, humanity will truly understand that all of Earth, every city, every forest, every ocean, is one shared home, protected only by a film of atmosphere thinner than a dream. This realization, known to astronauts as the overview effect, may evolve into something even greater, a planetary consciousness. As we build habitats on other worlds, we will also need to care for the one that gave us life. The fragility of Earth will no longer be an abstraction. It will be visible, hanging in the Martian sky like a memory. Yet silence also hides danger. In space, communication failures can mean catastrophe. A moment's loss of signal might separate life from death. This ever-present risk teaches humility. No matter how advanced our machines become, survival will always depend on cooperation, vigilance, and respect for the unknown. Over time, the settlers' children, those born away from Earth, may not feel this silence as loneliness. To them, it will be natural, woven into their sense of self. Their lullabies will be the hum of air filters, their constellations new, their definition of home broader. When they look toward Earth, they may not feel nostalgia, but gratitude for the planet that birthed a species brave enough to leave. And for those who remain on Earth, space will become less foreign, more familiar. The stars will no longer symbolize distance, but belonging. Humanity's presence across multiple worlds will redefine not just our geography, but our identity. Still, amid all progress, the lesson of the void endures, that silence has meaning. It is the sound of connection stretched thin but unbroken. It is the reminder that even in the coldest reaches, warmth can persist. It is the proof that home is not a single place, but a shared story, one that continues, orbit after orbit, generation after generation. When astronauts gaze out from their windows, when settlers walk beneath a Martian dawn, they will know the universe is not empty. It speaks softly through the silence, telling us that we belong not to one world, but to the vastness itself. And in that realization, the meaning of home will finally expand, from a planet to a principle, from survival to understanding.